to my Biochem series. In this episode, which is episode 13, we'll be talking about hypervalency. Now, we know a lot about these elements, hydrogen, carbon, nitrogen, oxygen, fluorine, but what about these elements? Silicon, phosphorus, sulfur, and chlorine. Well, today we're going to talk about it, but as a quick overview, silica is a brittle metal called a metalloid, which is in between a non-metal and a metal. There are many types of phosphorus. In this picture, we have red phosphorus, but there is also white and black phosphorus. With sulfur, it looks like a yellow rock, even though it is not. And chlorine is basically a poisonous green yellowish gas. This is the silicon with the subshells, so don't forget to check out that electron configuration episode, which is episode 12, the previous one. We now know that orbital shells can be broken down into subshells for a more detailed understanding. This is the simplified version. Aluminum, silicon, 2, 3, 4 in its outer shell. And if we add hydrogens, this basically looks like methane with the argon configuration. Here's this 3D structure. It looks like a methane. And it's basically because it's right below carbon, so it looks like methane, but this is called silane. Here's how you would draw it over here. But what if we add a bunch of this? This looks like a crazy mess, even though this is not very crazy. We have OH groups over here, also known as the hydroxyl groups. This is silic acid, also known as silicate. This is silic acid, the drawing, and here is the 3D model. Pretty complicated, huh? It's about to get even more complicated. Here's the silicate, the negative ions. Now, before I talk about the next thing, we should have this. So this is a 3D model of silane and primer. So this is silane. It looks like nothing, and this is pretty good. So now let's get back to the lesson. This is silica. Silica is a hard solid made from pure silicate. Minerals made of silicates, silica plus aluminum, sodium, potassium, calcium, etc. Most of the crust of the Earth and Moon are made of silicate rocks, fetched by mica, pure silica, and even the Moon. So when you're looking at the Moon, you're looking at this silica. Pretty cool, huh? White sand is made of tiny pieces of silicate rocks. So here is an image, silica. Glass is made mainly of silicate sand. Pretty interesting, huh? Sand and glass is the same thing, silica. Diatoms are single-celled algae with a silica cell wall. Silica cell wall called a frustule. The bright coloring is from chlorophyll and other pigments. That's extremely common and produce 20% of the world's oxygen. They have a cell wall made of silicon. In other words, they are made of glass. Very interesting. If you have a local pond, diatoms can clean this beach to reveal their beautiful silica structures. You can actually basically have a normal microscope, a normal one, and then wash it, and you can view diatoms under the microscope. Diatoms absorb silic acid from the water to construct the silica cell walls, but how they do this is still mostly a mystery for now. Now time to look at the electron configuration from row 3 elements. I still hope you remember how to look at the electron configuration. So, phosphorus and sulfur, 1s2s2 2p3 3s2 3p3, 1s2s2 3s2 3p4. This is simplified. Argon configuration. These are known as P3 and SO2, which the names I'm going to review in a second. This is phosphine, and this is hydrogen sulfide. Yes, hydrogen sulfide. Yes, hydrogen sulfide is the stinky part of sulfur. H2S is pretty stinky. Yeah, when you hear people say sulfur is stinky, it's the hydrogen sulfide that's stinky, not the element itself. Phosphine and hydrogen sulfide, these are both smelly. Indeed, very smelly. Some molecules seem to disobey our bonding rules. DNA's backbone has too many bonds. Look at this. Whoa. And sulfur and chloric acid digestive molecule has too many bonds. Wait. 1, 2, 3, 4, 5, 6. What? 5? Why do S and P have so many bonds? Like why? 3p electrons can bend with the 3D subshell. There's an empty 3D orbital over here, and therefore the electrons are very close, allowing them to blend in. Loose atoms with phosphorus, as expected, form 3 covalent bonds with the single electrons. But small atoms that have only positive nuclei F and O can force phosphorus with the separated lone pair and give away more electrons to bonds. Look. This electron gets promoted to the D orbital. 1, 2, 3, 4, 5. Now, this is phosphorus pentafluoride. Oh my god. Very complicated. Well, it's about to get even crazier. Phosphoric acid. Oh yeah, you use phosphoric acid. This is the simplified. Well, it's not very detailed. You see, we get some scandium. So here's the electrons, and now here is phosphoric acid. We have this double bond right over here. Over here is a double bond. Acids with more than an octet are hypervalent. That's the name of this episode. Well, yeah, because it is about hypervalency after all. H3PO4 has 10 other electrons. That has the awkward configuration. Yeah, anyway. This is phosphoric acid, phosphate, phosphoric acid, phosphate. DNA and phosphate charge. Notice that the phosphate backbone with DNA lost a proton, so has a very negative charge. Very negative. DNA's backbone is super negatively charged. Most atoms bond with sulfide scripted, forming 2 covalent bonds with the 2 lone electrons. But, like phosphorus, these electrons get promoted. Now we have 1, 2, 3, 4, 5, 6. They get promoted to this empty 3D. And voila! 6 bonds. Sulfur hexafluoride. Didn't see that coming, huh? Very funny. This is sulfuric acid, which you might have heard of, is a super acid. You might have heard of it, and it can become sulfate. And sulfuric acid is very common. So, here we have the electrons counting. And then here we have it. Sulfuric acid. 12 out of electrons. What in the world? Yeah, what in the world? Yeah, seriously, this is very awkward. But still, sulfuric acid and sulfate. Tarocolic acid charge. Tarocolic acid also lost a proton, so it has a negative charge. Predict the hypervalency of chlorine. Now I'm going to give you a few moments to ponder this. Feel free to pause the video. Well, it seems like you figured it out. The answer is perchloric acid. What? Yeah, like seriously. What? Yeah. How many bonds are there? There are 1, 2, 3, 4, 5, 6, 7. So here is the liquid fuel rocket. In the solid fuel rocket, it is combustion. O2 plus H2 equals this. But in this, we have ammonia plus perchloric acid equals hydrochloric acid, oxygen, nitrogen, and water. Hydrochloric acid. Most atoms bond the sulfide expected, forming 2 covalent bonds with the 2 lone electrons. But small atoms, oh my, 7 CC. But however, they cannot make COSs, but they have been able to make IF7. Not possible yet, but look, iodine hexafluoride perchloric acid. Seriously, what are you doing about? Like, this is very crazy, as you can see. The electrons can literally go there. Oh my god, this is seriously complicated. Here we go. Oh my god, this is perchloric acid 14 at electrons. What? Oh my god, we're getting mixed up. And they can have a negative. Proton can lose 1 proton, making a single acid. So here's the periodic transfer. Rows through elements. What periodic trends do you see as we move from silicon to phosphorus to sulfur to chlorine? Give it a few minutes to ponder it out. Well, you see the thing? Well, this is it. And this is, I'll see you later for episode 14. Goodbye. See you later. Bye for now. Don't forget to subscribe to my channel. That helps me a lot with my videos. Bye-bye.